this is the low frequency level. So that is a stop band. Here also high frequency level. This is also a stop band because we are not interested to receive these frequencies at the output. We are interested with only this specific frequency level. That is the this is the cutoff frequency F1 and cutoff frequency F2, or we can also say this is a FL and this is the FH, lowest cutoff frequency and highest cutoff frequencies or frequency. And this is the so between them it's called pass band. So this is the frequency response we want, but we want as sharp as possible. We want sharp rising and we want sharp falling. But here you can see it's going slowly, linearly it's increasing and it's linearly falling down. So we want sharp one. So in that kind of situations, what can we do? We have to go with the higher order filters. So we have to cascade more number of stages. Then we will get, when we go more and more higher number of orders, then the falling off will be more sharper or the rising will be more sharper. Okay, so here you can see this first cutoff frequency. This is from minus 3 dB. So this is the 0.707, or we can also call this as a 1 divided by square root 2 times of Bn. So then here you can see this is the frequency level. If so, it just gives the frequency level FL. This FL value is depending upon the resistor and capacitor value you are using in the low pass filter design. So here we have the low pass filter, right? So here you have the R2 and C2. So depending upon this R2 and C2, this cutoff frequency will be vary. So for example, here FL is equal to 1 divided by 2 pi RC, right? That is the general formula for the cutoff frequency. So here is R2 C2. Okay, so this is the FL and FH. Also we have a cutoff frequency. We can calculate using the same formula, but instead of using this R2 C2, we have to use R1 C1. So 1 divided by, so this is the FH is equal to 1 divided by 2 pi R1 C1. So these are the capacitor and resistor is used in the high pass filter section of this band pass filter. So now we have two cutoff frequencies and we know this either rising or falling is following this Bode plot, because this is minus 20 dB per decade. So first of all, this minus 20 dB per decade. So this one you should understand. We will see Bode plot maybe in the upcoming lectures. So you will understand how to calculate this minus 20 dB per decade. What does it mean? So mostly we calculate the amplitude or the magnitude of the signal with respect to with respect to frequencies. So that's why we have in the x-axis we have frequencies. This is the angular frequencies in hertz. But in the y-axis, we always have this in terms of dB. dB is nothing but a transfer function. So we know V out by V in is equal to A. That is the gain. So we can also call this as a transfer function. So when we take this with respect to log, then we will get this value. This is in all the plots for frequency response analysis, we will use this standard method of plotting the graph. So this is indicating the amplitude of the output in terms of dB. And this is the first part of the graph. This is only talking about the amplitude versus frequency. But the second part of the plot is talking about phase with respect to frequency, or phase versus frequency. So here phase, the unit is degree, and the frequency, we know that the unit is hertz because it was invented by the person Hertz. So the unit is hertz now. Okay, so here you can see FL and FH. We have two cutoff frequencies in this band pass filter. So in the middle, we have the center of the frequency. So this is called the F center. So at this point, here you can see the frequency, the output signal phase is changing. So it's just falling down slowly, and then it will meet 0 at this center frequency. And then the phase will go in the opposite direction, and then it will rise to another minus 90 degree. So this is the this is how the band pass filter is working. So you can immediately or by default you can say at the center of the cutoff frequency, this phase will go to 0. Okay, so here we can just read this on time. We can simply define the term bandwidth. This is the bandwidth. It's the difference between lower cutoff frequency, that is this one FL, and the higher cutoff frequency. And higher cutoff frequency, that is called bandwidth. This is the definition. In other words, BW, that is the bandwidth, is equal to FH minus FL. So maybe you may have some problems to find the cutoff frequencies of band pass filter and find the bandwidth. So this is the very straightforward formula. It's not very complicated. So it's just the difference between these two frequencies, because that is what is passing and we are getting at the output of the filter. So clearly for a band pass filter to function correctly, the cutoff frequency of the low pass filter must be higher than the cutoff frequency of the high pass filter. It's just one condition, because what is the formula? Okay, here we have the FH minus FL. So one frequency must be higher and another frequency will be definitely less. Then we can find the difference, that is going to be the bandwidth. So the Bode plot we had seen already. So you just try to remember stop band and then the pass band. Pass band is nothing but the bandwidth. So bandwidth is the difference between FL and FH. So FL minus FH or FH minus FL. So the difference. And the y-axis is the gain in terms of dB. The gain is nothing but the transfer function. So we have to take the logarithmic, and then we will get in terms of dB instead of in the V out in Vn, V out divided by Vn. So in the later lecture, we will learn about Laplace transform. Maybe in the mathematics, you have already studied about the formulas of this Laplace transform, how to convert the signals. For example, you have one function with respect to t is the time domain, and then you have to convert this into the s domain, function of s. So function of time domain, you have to convert into function of s domain. S means what? That is just a sequential domain, or we can also call this as a frequency domain, because whenever you give input to one system and you are getting output, right? This is the standard one. And at the output, we need to analyze what is the amplitude we are getting at the output. So the amplitude is definitely, it's going to be different from the input. If you apply 10 volt at the input, at the output, maybe you will get 9 volt. But if you use the amplifier in between, instead of 9 volt, maybe you will get maybe 15 volt or 10 volt, 11 volt or 20 volt. It's depending upon the gain of this amplifier. So here the amplitude got changed from the input level. So we need to analyze this mathematically. So if you are only talking about, okay, so you are applying this input at time point T1 and you are getting at time T2, 9 volt or 15 volt, right? So if you only analyze with respect to this time, it's going to be more and more complicated. That's why we have some mathematical transformations. Like we can use the Fourier transforms, we can use these Laplace transforms. So these kind of transforms are helping us to analyze these signals, not only with respect to the time, with also respect to the frequency. Because whenever we apply this 10 volt, the frequency can also get changed at the output. So that's why we are going to this Bode plot. So now, since we did not see the Bode plot yet. So just remember, this is how it works. We will see in the later lecture about Bode plot. How can we make this Bode plot? How we can calculate this in terms of dB by using logarithmic table. Okay. So this is why we are going to this Laplace transform actually. So for example, you have let's say this circuit. So you are applying the input and you are getting the output. So the current is flowing through each branch, and you have the voltage drop or voltage potential across each component. So if you want to calculate this, maybe you can just use the circuit theory. Kind of, you can use the nodal analysis or mesh analysis, and you can find the current and voltage across each component, right? Maybe you have studied this already last year in the network theory or circuit theory. So this is really you are calculating with respect to time. So now we are going to do the same with respect to frequency. So that is what the Laplace transform is going to help us. Okay, so this is the frequency response of the band pass filter. And the signal is attenuated at low frequencies with the output increasing at a slope of plus 20 dB per decade. So this is this one until the frequency reaches the lower cutoff frequency point, that is the FL. So until it reaches this point, it's just raising linearly, but this is plus 20 dB per decade. Okay, and what remember, so we have this decade and octave. So everything is multiplied by 10. So that is what I said, like when we see the Bode plot, we will see the detail of this decade and octave. But right now, just remember this. This is a raising plus 20 dB per decade. So at this frequency, the output voltage is 1 divided by square root, that is the 0.707. In terms of percentage, that is 70.7. So this point. So this is the 1 divided by square root or 0.707. If you make in terms of percentage means we must multiply by 100. So then it will become 70.7. So at this level, already the frequency response rapidly changes and it becomes flat. So this is the output, maximum output. This is what we want at the output of the filter. So we want only this flat maximum output. Okay, so at this frequency, the output voltage gain is this one of the input signal value. So as I said, like this is this one and then multiplied by V in. Then you will reach this point. So, okay, and 3 dB, this 3 dB, how can you calculate this 3 dB? So this 20 times log of V out divided by V in. So V out value, we know here, you can measure the amplitude, and the V in, that also you know how many or how much voltage you are applying at the input. So then you can calculate this. It will become actually minus 3 dB or 3 dB signal. The output continues. The output is still continuing at maximum gain until it reaches the upper cutoff point or upper cutoff frequency. So this just will travel flatly like this until it reaches this higher cutoff frequency or upper cutoff frequency. After this FH, the output will start to decrease. That is going to be minus 20 dB per decade. So it's rising plus 20 dB per decade, and then it becomes flat, and then it just increasing. It after the frequency reaches this maximum cutoff frequency, then it will fall down. So then we can say until we reach this lower cutoff frequency, this is the attenuation part. We are blocking the frequencies and we don't get the output. Similarly, here we are getting the output. So this is called a pass band or band pass. And after this higher cutoff frequency, again, we are blocking the frequencies so we don't get the output. So output is 0. We want ideally 0, but it's not really ideal 0. It's just you still have some output value. For example, let's say here, if we talk about in terms of voltage, this is the 0 volt. Maybe output you are expecting 10 volt at the maximum level, right? So you want like this, but here you can see maybe the output is here, like still you are getting like a maybe 3 volt, or maybe here maybe you are getting 5 volt. Some output you are still getting in the stop band that we do not really want. So that is why we are talking about the higher order filters. So we want to make this as sharp as possible, like this. Okay, so the center point of maximum output gain is generally geometric mean of these 2 minus 3 dB values between the lower and upper cutoff frequencies. Okay, this is the center frequency that we know that. So this F center is exactly in the midpoint of this FL and FH. Okay, so this is also called as a resonant frequency. So remember, this center frequency is called a resonant frequency, F resonant. So this one also have a formula how to calculate this mathematically. So F resonant is equal to F R square is equal to F upper multiplied by F lower. So if we talk about this FL, FH, both are same. The upper is just H and the lower is just L. So how can we calculate this resonant frequency? FR is equal to square root of FL times FH. Or we can also call this as a FR square is equal to FL times FH. We can represent in any way, but how to calculate this FR resonant frequency? This is the formula. If it's a second order filter, it means 2 poles. We have 2 stages of the band pass filter. Then because it has 2 reactive components within its circuit structure, then the phase angle will be twice that of the previously seen. Okay, the first order filter, of course, you are getting 90-degree phase shift. And if you use the second order filter, then you will get this 180-degree phase shift. The phase angle of the output signals leads that of the input by plus 90-degree up to the center of up to the resonant frequency. So here it just leads 90-degree. You can see here, this is the upper part, this is the positive side, and this is the negative side. So this is what we call the output is leading 90-degree. The output signal is leading by 90-degree up to the center frequency, and after that it start to lag. So this is the lead part plus 90-degree, and this is the lag. So this is what mentioned here. So until reach this center cutoff frequency of the resonant frequency, after that, of course, at this center or resonant frequency, it becomes 0 degree. In this, we are talking about with respect to phase angle. So this is 0, and then after this 0, after this resonant frequency, then this phase angle is going to just in the opposite direction. So it's going to lag 90-degree. So you can just read this paragraph. Yeah, so this is what mentioned here. So this is 90-degree leading, 90-degree lagging, and at the center of the frequency, the phase angle is 0. So now upper and lower cutoff frequency, the formula is the same, 1 divided by 2 pi RC. So as I mentioned here, so 2 pi RC, so it's For example, if this is going to be the upper cutoff frequency that is based on this high pass filter, that is 2 pi R1C1. The lower cutoff frequency is based on these low pass filter components, that is 1 divided by 2 pi R2C2. But the formula is the same. And so here I want you to remember this cutoff frequency formula. And I want you also to remember this resonant frequency formula. FR is equal to square root of FH multiplied by FL. Of course, if you make square, then this square root will this will be gone. So you can remember either way, but this is the better way. So instead of FR square, you just remember this FR is equal to FL times FH under square root. So here is the small problem. A second order band pass filter is to be constructed using RC components that will allow a frequency range to pass only like above 1 kilohertz. This is the okay. The starting level is 1 kilohertz or 1000 hertz, and below 30 kilohertz or 30,000 hertz. And assuming that both the resistors have values 10 kilo ohms, calculate the value of two capacitors. So here we know the resistors R1 and R2 10 kilo ohms, and we also know the frequency, that is the FL and FH. We know that. So this is the lowest cutoff frequency and highest cutoff frequency. And if you minus this, then you will get this bandwidth. Okay. So then you have to calculate the value of this C1 and C2 to design this capacitor. To design this band pass filter. So the high pass filter stage, of course, this is high pass filter, right? This is the total band pass filter, but we can divide into two sections. The first section is high pass. So the value of the capacitor C1 required to give a cutoff frequency FL, that is the 1 kilohertz, they had already given with a resistor value of 10 kilo ohm is calculated. So we know the formula for FL. FL is equal to 1 divided by 2 pi RC. So here R1C1. So they had given this resistor value as a 10 kilo ohm. So we have no problem. And the C value we don't know. So then we can just bring this C to this side. That is what done here. And then 1 divided by 2 pi, lowest cutoff frequency, that value we know that. And then the resistor value is 10 kilo ohms. And then we can calculate this capacitor value. So then these values R1 and C1 required for the high pass stage of this band pass filter. So of course, this is the 15.9 is the exact calculated value, but practically the available value is 15 nanofarad. We do not have anything like 15.9 nanofarad. So it is just, we are rounding off this value to this available capacitor value. But in the problems, when you solve, you can just write this one. This is enough. And low pass filter stage, the same. So we already know the upper cutoff frequency, that is the 30 kilohertz, and apply the same formula. So we don't know the C2 value, bring the C2 here, and then apply the numerical values, then you will get this C2 value. So now you know C1 and now you know C2. You also know R1, R2 because it's already given in the problem, both resistors. So now you can design this filter, and you know this lowest cutoff frequency and highest cutoff frequency. Then you will get the exact band you want. So the same formula here. So now you know the values of C2 and R2 required for the low pass stage. That is the low pass filter stage to give a cutoff frequency of 30 kilohertz. Okay. So however, the nearest preferred value is 560 picofarad. This is also just close to the practical available capacitor value. So with the values of both the resistances C1 and C2, so this we know that, and then the capacitors value we know that. So now you can construct this circuit like this. So now I ask you one question. Can you find the FR value? So you know this FL and you know FH. Can you please find this FR? So you know the formula for FR also. FR is equal to square root of FL times FH. So what you had done is, you know the frequency values and you know the resistor values. You have found the C1 and C2. So now you have to find the FR value. So FR is like this, the formula. So the lowest cutoff frequency is 1000 Hertz and the highest cutoff frequency is 30,000 Hertz. So of course, this, if you calculate why I got this value, after I found this resistor and capacitor value, if I calculate this FL, I get this one. So I just apply this 1 divided by 2 pi R1 C1. Then I get this 1060 and here 28,420. So this is not ideal value. So this is the practical value because I have adjusted the capacitor value. So this is the lowest and highest cutoff frequencies, and I can find the resonant frequency very easily. So that's all about this passive band pass filter.